Director of IronFlux Product Development at Fluxion Biosciences. After these two great talks before me, I would like to expand a bit about the capabilities of the IronFlux system for enhancing PAM assays development. First, a bit of background about Fluxion Biosciences. The company was founded in 2005, and our headquarters are in South San Francisco in California. Being a small company, we have many distributors worldwide, and the company won 5 NIH grants and 2-time R&D 100 awards for Bioflux in 2008 and IronFlux in 2010. We have 3 main product lines, all based on microfluidics technology. Bioflux, used for live cell imaging under flow, IronFlux, our offering to the automated patch clamp arena, and IsoFlux, a microfluidics-based CTC isolation system. Now, the IronFlux system is built by Fluxion Biosciences, but distributed and supported by Molecular Devices. The IronFlux is, by simple terms, an automated patch clamp system based on a unique in-plate liquid handling or solution movement strategy. The system does not require a complicated liquid handler to move solutions and hence has a footprint of a simple plate reader. It comes in 2 main flavors, IronFlux 16 with 16 amplifiers, which is a great entry point to automated patch clamping, and an IronFlux HD with 64 amplifiers, a great contender and step towards the medium EFIS high throughput market. The lack of liquid handler allows both IronFlux 16 and HD to be quite competitive price-wise and great value for investment. Okay, however, effect on system pricing aside, this lack of dedicated liquid handling is actually the end result of the IronFlux's unique ability to move solutions inside of the recording plate itself. The machine uses standard SPS plate formats, 96 wells for IF16 and 384 wells for IronFlux HD. But the difference is that the bottom of the plate has been replaced with an intricate laminar flow system, providing an integrated cell and compound delivery as well as recording. Looking at the bottom of the IronFlux plate in more detail, the plate is divided into patterns, as you can see here. Zooming into one of these patterns and then flipping it to look at it from the top, the pattern is composed of 12 wells, 2 independent recording wells connected to separate amplifiers. These recording wells, also called traps, would contain the intracellular solution, an inlet well where the cells in extracellular solution are introduced, an out or waste well, and 8 different wells where different compounds and solutions can be added. We have 32 experimental patterns per IronFlux HD plate and 8 patterns per IronFlux 16 plate. The design of the plate and the intra-movement of the solutions allow for independent compound conduits, hence no mixing, no cross-contamination, no pipetting delays, and no electrode-compound contact. The microfluidics design was featured on the cover of Assay for August 2012. We like to show this all the time. We also had an article in that issue, but nevertheless, the cover is beautiful on its own, as you can see. Okay, now looking closely at the mechanism of action. Once plate is filled, it is introduced into the machine. The start of the assay begins with priming of the microfluidics. After that, the cells with extracellular solution start flowing through the main chamber until trapping occurs. And seals are formed. And then afterwards, extrasuction opens the cells and recording begins in whole cell patch clamp mode. So a typical experiment would involve opening of the compound pneumatic valves, allowing the release of the compounds into the main channel, flowing continuously towards the cells. The independent control of these compound inlets provides fast and successive compound additions, as well as continuous compound washing in between the compound additions. Consider that these wash steps are not really steps, but more like washing gaps in between the compound release from their inlets. So this will become clearer later on. It is important to note that the reliance on pneumatics instead of physical robotic liquid movement provides the parallel release of all compounds at the exact time. So the whole plate is done all at the same time. Hence, one experiment or 32 experiments will take exactly the same time to complete, allowing the IronFlux assays to complete larger experiments very quickly. Okay. Now, as mentioned, the IronFlux plates record from cells in whole cell patch clamp mode. 2 types of plates exist. Ensemble plate with 20 cells per recording. Those are the most common ones. And single cell plates, which a lot of people use also for different needs. Ensemble plates are designed for high quantity in mind, where currents from all cells are added, not averaged. And single cell recordings are meant for highest quality, where cells are patched and sealed with gigaohm seals. Let's look back at the solution movement and its control within the plate, since that's the most important aspect for PAM studies. Similar to what you have presented before, the Influx software provides an extensive graphical control over the delivery of compounds and solutions. To start, the start and end time of the release of a specific compound is simply drawn in the software. Separating the steps would mean washing of the cells. The longer or shorter the distance between the steps, the longer or shorter the wash step. In fact, we can get the steps so close to each other that no washing occurs. Since this is a continuous flow system, washing is continuously going. You just need to factor it into your assay. Here we step from one compound to another instantly. Again, all that is happening in parallel within the plate. Although these steps are of exact size here, you have complete control over their lengths and can even superimpose them, just like what Juha showed. This ability shows off the true capability of the system's fluidics. For example, we can have two compounds flowing at the same time, here from well 2 and well 3, with the cells only seeing the compounds flowing from well closest to them, here well 3. Then we have an interruption in the flow of well 3. The compound from well 2 would fall on the cells nearly instantaneously. This flexibility in compound displacement provides extensive capacity in development of difficult ligand-gated assays such as PAM assays and double agonist assays. I'd like to show you a few examples of such assays using GABA receptors modulation as targets. To start, we have used hex cells expressing GABA-A receptors, here alpha-1, beta-3, gamma-2, millipore urafin precision cells. The plot shows serial sweeps from the same recording while superimposed demonstrating the agonist activation of the receptor. Now these are serial sweeps, so this is like one sweep after the other in the same well. When compiled together, a dose-response curve can be plotted showing an EC50 of 3.32 micromolar, which is consistent with published values. This is N equals 40. Now the receptor is sensitive, of course, to a number of agonists, including GABA, muscimol, and isobutyrin, and even ethanol. Here is the response to 3 micromolar muscimol and 3 micromolar GABA and 3 micromolar isobutyrin, showing the different potency of the 3 different compounds. Now here you can see actually that potency for muscimol was higher than GABA, higher than isobutyrin. Again, the EC50 values were consistent with published results. Now, just to establish our baseline with regard to our assays, it is important to note that both positive allosteric modulator and the agonist are needed to initiate a response. An agonist alone can open the channel with the PAM increasing the effect of the agonist. However, if the PAM is added by itself, no response is seen. Hence, to study PAM effects on receptors, the baseline effect of the agonist need to be consistent and repeatable, in addition to the already mentioned highly flexible and speedy liquid control. So we really need to establish the repeatability of the baseline response. So here, what we're looking at, we're looking at the repeatability of the baseline response with regard to GABA. The rapid control of solutions as well as the continuous flow of compounds provide the influx with consistent response to the same agonist addition. So although we may have differences in the total value of the current, the sweep-to-sweep variability is basically minimal. Here we see 2 recordings wells receiving 10 micromolar GABA. Notice the currents are not of the same size since they come from different wells. However, sequentially, variation from sweep to sweep is nearly minimal. This can be observed more clearly with this IT plot. So just to explain about these IT plots, which are actually seen live when you're actually recording from the influx. This is a plot of values seen by placing cursors in the software at specific location in the sweep run. So within these sweeps, 2 cursors are placed, one before the addition of GABA and one after it. The cursors measure mean current and the values are subtracted. When GABA is added, a response is measured and a negative point is recorded. When wash steps are followed, no response is seen and a 0 value is recorded. So this repeatability and consistency of response is crucial to establishing a baseline for the study of PAM effects, since sweep-to-sweep response to GABA would become our control. Okay. So once we establish repeatability and consistency in basal GABA response, we can look at the effectiveness of the successive serial additions in PAM assays. In this experiment, we first had 1 micromolar GABA added, establishing a baseline response to agonist. Next, 0.05 micromolar diazepam is added and incubated for 1 minute. As expected, no current is observed. However, when diazepam and GABA are co-applied, a slight increase in the current is observed. Next, another incubation phase is performed, but now with 0.15 micromolar diazepam, which also shows no evoked current. Finally, 1 micromolar GABA with the 0.15 micromolar diazepam would result in current which is substantially larger. So all of this, again, is serial, is one after the other, with no watch steps in between. It just goes on. Here we have the successive superimposed sweeps from the same recording wells showing the effect of increasing diazepam concentration on GABA currents. The baseline is established again with 1 micromolar GABA, followed by 0.05 to 20 micromolar of diazepam. We also tried PAM of the same benzodiazepine family like triazolam. Note that the higher potency of triazolam as compared to diazepam and the distinctive effects on receptor potentiation. Now, the EC50 of diazepam, zolpidem, and triazolam, and zolpidem is actually marketed as Ambien. I can see the commercials for it most of the time on TV, and is outside of the benzodiazepine family. Experimental values were 425 nanomolar, 84.6 nanomolar, and 12.1 nanomolar, which are in agreement with literature. Note the increase in potency of triazolam followed by zolpidem and diazepam. Now, the pneumatic control and the in-plate solution movement allows the influx to have the feasibility for automated assays that are challenging on systems which are mostly dependent upon liquid handlers to move solutions. Looking back at the example compound addition map from before and considering that the activated GABA-A receptor current shows a fast activation followed by a slow deactivation, it is possible to sequentially increase the agonist dose faster than the rate of deactivation, effectively increasing the activation of the current in a staircase effect. If all timed correctly, a current staircase would be seen with the same sweep in response to increase in agonist concentration. An example of this, the staircase activation is shown here. The receptor was activated with 1 micromolar GABA, followed by 3 micromolar GABA, and then 10 micromolar. The compounds are applied for 2 seconds at each concentration. Here we have response for 2 wells. An interesting part of this assay is the ability to obtain a quick EC50 from a single sweep. Again, this is not calculated current versus time achieved by obtaining multiple sweeps. This is a staircase increase in 1 sweep. Now, to show the potentiation effect of PAM, a similar experiment is conducted where a constant application of modulator is added and compared to control. Here we have the same staircase GABA activation with and without the application of 3 micromolar diazepam, clearly showing the expected allosteric shift in current magnitude. Now, of course, this is similar to what Juha has talked about before. It's relating, so these rapid liquid displacement assays can also, of course, be seen for the open channel modulation assays. And here looking at an open channel assay similar to what Juha showed. In this example screenshot, cells were perfused in 1 micromolar GABA for 4 seconds, then switched, that's where the arrow is, to a GABA diazepam mixture solution for 8 seconds. Different traces in the graph are recordings from 16 different cells ensemble. The effect above shows the open channel potentiation of the receptor, and of course the assay can be expanded to other PAM targets. Another example, here is an overlay of DMSO control in red, in green showing GABA application for 8 seconds, in blue GABA for 4 seconds, then GABA plus diazepam for 8 seconds, and in orange GABA for 4 seconds followed by GABA with a blocker, here picrotoxin for 8 seconds. All of the above experiments were done within the same plates and at the same time, again with all of the steps within the same sweeps. Okay, these assays can be used to investigate other targets, of course. So now that we have established that we can do all of these fluidics and all of this movement of solutions, what about more difficult targets? For example, NMDA double agonist. So this is actually, I'm just going to show you this slide, which is very similar experiment. Here, a cumulative concentration response with NMDA. Shown are 16 ensemble recordings from a single plate. Glutamate concentration is increased with basal concentration of 30 micromolar glycine. As glutamate is increased, the response is increased. It is important to note that NFDA experiments do benefit from enhanced fluidics of the on-flux system and the continuous flow. Considering that these experiments are quite difficult in stagnant solutions due to the open channel toxicity of NFDA receptors, which is induced by local production of glycine and glutamate from neighboring cells. So as summary, the on-flux system, equipped with its unique liquid exchange and continuous flow, provides an excellent platform for complex PAM assays. The ability to provide a consecutive and fast switch from one compound to another or to serially increase compound concentrations with no wash steps or liquid stacking problems gives the platform the unique edge and speed a complex PAM qualification assay would require. Thank you. Jim, you can take it back.
Thank you, Ali. Thanks for walking us through the IronFlux instrument and its capabilities. I have to say we really enjoy working with you and with Fluxion to bring customers the IronFlux technology.
Same here.
With that,